Hi everyone, in this video we are going to discuss how to actually quantify the heat flow from a system to the surroundings in a calorimeter. How cool, right? Okay, maybe not, but that's okay. We're going to work through it together anyway. So let's start off by talking about what a calorimeter is in a very, very brief, very simplistic version. So we need to have a system. Remember, a system is basically just your sample. So you have a sample, it's a piece of cake, it's a fuel source, a lot of times in this course, it's actually a hydrocarbon. Okay, so you have a system. We put it inside of a calorimeter. Everything except for the system is considered your surroundings. So all we're trying to do is quantify the amount of heat that is transferred from the system to the surroundings. So that transfer of energy is we just want to put a number on it. Okay, so how do we actually do that, right? What we do is we have this beautiful equation. So we have Q is equal to MC delta T. So let's go through each one of these variables and just get ourselves back up to speed. So Q is heat. Remember, Q is not temperature. These are very different things. T, capital T, that's your temperature. So now heat is your measure of your transfer of energy in the form of heat. It is always from a hot object to a cold object, but this is an energy term. So we use joules as our unit most of the time for this equation. Now, for temperature, we are talking about the measure of kinetic energy at a very specific unit of time. And so when we talk about temperature, our units are typically Kelvin or Celsius. Now, something else I want to point out, we have a delta here. This is actually a delta T, so our change in temperature. Anytime you see that delta, you should immediately be thinking final minus initial, always. So that means it's your final temperature minus your initial temperature of your sample. All right, so we've taken care of Q, we've taken care of T. We already know what M is. M is mass, and we know that most of the time with mass, we're going to use a unit of grams. So this is just the amount of mass or amount of your substance or amount of your sample, okay? Last one we have is C. Now, C is a new one, so let's break this down very, very slowly. So C is called heat capacity. And so now what I want to do is actually make it more specific, and we're going to do that by adding the word specific heat capacity. And when we do that, we're going to add a little s right there. So specific heat capacity, which is big C, little s. Now make sure you get this definition down. It is the amount of energy that is required to raise 1 gram of sample. It is very, very specific. That 1 gram is actually why we use the word specific. So 1 gram of sample by 1 degree Celsius. Now, I'm also going to say it could be 1 Kelvin. It just depends on how your constant is given to you. So let's talk about this. This is saying how much energy is required to raise 1 gram of sample. Let's say our sample is a chunk of water, okay? We have a gram of water. How much energy is used to raise the temperature of our water from, let's say, 25 degrees Celsius to 26 degrees Celsius. We're just saying how much energy. And so this typically has a unit of joules per gram degrees Celsius or joules per gram Kelvin. This one right here is our main one, but you need to be comfortable with both. So let's just work a couple examples here to try to get comfortable with this equation as a whole. All right, so let's start off with a simple one. We have a piece of lead, and we're going to say we have 150 grams of it. We're going to say it's at 100 degrees Celsius. So the initial temperature of our lead is 100 degrees Celsius, okay? And we're going to say that this is placed into a calorimeter. I'm just going to say CAL, okay, calorimeter, releasing 1.37 kilojoules of energy. We're going to have to tell you that the specific heat of lead is equal to 0.128 joules per gram degrees Celsius. Now, my question here is, what is TF? What is the final temperature of your lead sample? Okay, so we're going to work through this together. I'm not going to make you do this on your own yet. Haha. Evil. Okay, so now Q is equal to MC delta T. Q is our heat transfer. That's this part right here, the 1.37 kilojoules. But I'm actually going to underline the word releasing because that's super, super important here. If we say the word releasing, you need to have a red flag go off in your head that's going ding, 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 ding. That means we are going to have a negative value for Q. You have to get this down. If we say releasing, it's going to be negative. If we say absorbing, it's going to be positive. So this is negative. Now, our specific heat was given to us in joules, so we need to get out of kilojoules kilojoules and into joules. So we're going to say 1,370 joules of energy equal to our mass of lead. Now we have 150 grams of lead. We know that. That was given to us. Specific heat, we're going to say C sub S. That is going to be 0.128 joules per gram degrees Celsius. Now times our temperature. Final minus initial. We're solving for our final, and we have to determine what our initial was, but that was given to us. We know that we started off at 100 degrees Celsius. All right, so all you have to do is plug that into your calculator properly. And if you do, you will get a final temperature of something like 28.6 degrees Celsius, okay? Pretty straightforward. Now, if you had forgotten this negative sign, you would have had some very, very odd number here. And if you try this problem without the negative, you would see right away this just doesn't make sense. So always check your answer. Make sure logically it makes sense that the temperature went down. And it does. If we put a hot piece of metal into a big vast of water, we know that the temperature of our metal would decrease. That makes sense. This is logical. All right, so now we're going to put a part 2 of this problem. So now we're saying, instead of A, let's say the calorimeter contained, we're just going to say 50 grams of water. Okay, calorimeter has water in there, about 50 grams. Our question now is, what was the initial temperature of the water? So we know what the final temperature is. We put the metal in there, we put the water in there, they reached equilibrium. So the final temperature of our solution, so that's of our lead and our water, is 28.6 degrees. Now I have to tell you what the specific heat of the water is. Without this number, you could not do this problem. So that's 4.184 joules per gram degrees Celsius. All right, so let's do this one together. So same equation, Q is equal to MC sub S delta T. Q is the same number. It's the exact same number. But now we're talking about this from the water's perspective. We're no longer talking about it from the lead. We're talking about it from water. Lead was our sample. Water's our surroundings. And so our heat transfer went from the lead to the water. So it was given off, exothermic lead. It was absorbed by the water. Okay, so positive for this term. So positive 1,370 joules of energy for our heat. Mass of water is 50 grams. Specific heat of water is 4.184 joules per gram degrees Celsius. And now we're trying to determine our initial temperature. So our final temperature was given to us. Well, we actually just solved for that, 28.6 degrees Celsius minus our initial temperature. So in theory, I could have given this to you as one giant problem, and we could have asked you to solve for the initial temperature of the water, and you could have done that all on your own. So now the initial temperature, if you've done this properly, is 22.1 degrees Celsius, which again, check that. Does that make sense? You had water, you threw a piece of hot metal in it. Would it make sense for the water temperature to increase a little bit? Yes, it definitely does. It would go from 22 degrees to about 28 degrees. That makes sense logically. All right, so now we have one more problem. This is the one I'm going to want you to do on your own. I'm going to write it out. It's long, so if you need to zip ahead in the video just to get to the question, that's fine with me, but otherwise just stick with it here. All right, so we have 20 grams of aluminum. The aluminum is at 98 degrees Celsius, and it's placed in 50 grams of water, okay, again, in a calorimeter, releasing, important word, 1.29 kilojoules of energy. Now, the final temperature of the water was 26.5 degrees Celsius. The question is, what is the specific heat of aluminum? So I'm asking you to solve for C sub S for me, okay? Go. All right, did you get an answer? Hopefully you did, but just in case you didn't, let's go through this together. So we have Q is equal to MC sub S delta T. So now let's start off with our heat content. So Q, we know that we are releasing, so releasing, that's negative 1.29 kilojoules of energy. Right away you should be thinking, I want to get this out of kilojoules, let's just put it into joules. All right, so we have negative 1,290 joules of energy equal to your mass. Now, what mass are we, what is our system? The most important thing you can do here is assign a value to your system and be consistent. So we're looking for our specific heat capacity of the aluminum. So our mass has to be of the aluminum. If you put the mass of the water there, it's not going to work. So we have 20 grams of aluminum. We're solving for the specific heat of our aluminum. Now we can do our final temperature minus our initial temperature. All right, so our final temperature of the water was 26.5 degrees Celsius, right? Our initial temperature was given to us at 98 degrees Celsius. Final minus initial. All you have to do is solve that out for your specific heat. If you do that properly, you get an answer of 0.902 joules per gram degrees Celsius. Did you get that? Hopefully you did. If not, practice, practice, practice. Bye, guys.